So black holes exist, and they are an important part of the constitution of galaxies, and they are the endpoint of stellar evolution for massive stars, and most of them we don't see, but if they happen to have a binary partner, we can detect the accretion disks around them. Okay, what can we say about these objects from understanding GR? What do people's studies tell us? The black holes we've been considering have been the simplest, spherically symmetric, non-rotating, simple objects. How complicated can black holes get? Well, they get complicated, but it turns out not very. There's a beautiful theorem known colloquially as the black hole no hair theorem, or a black hole has no hair. It turns out that in the collapse from a star to a black hole, all the properties of the stars are lost. The chemical composition makes no difference. The temperature is gone. The shape of something that collapsed is gone. All of those features are radiated away as gravitational waves or energy. All that information is gone in the collapse. Black holes are completely characterized by 3 numbers. Tell me 3 properties of a black hole, and I can exactly describe. That is all there is to say about it. We said that stars are by and large described by mass, but stars also have magnetic fields and rate of rotation and chemical composition and metallicity and age. No such thing for a black hole. A black hole is completely characterized by its mass, its angular momentum, and its electric charge. Now, electric charge is expected to be 0. Why would a black hole carry an electric charge? Everything in the universe is pretty much neutral. We know about its mass. We can measure it if something's orbiting it. Angular momentum is expected to be rather large. Remember, this is a collapsed neutron stars. These neutron stars we saw, or the collapsed core, when it collapsed to a neutron star, it carried enough angular momentum to drive a pulsar. We expect most black holes to be rotating rapidly. The Schwarzschild example that was the topic of the simulations we've been doing was a simplified case with vanishing angular momentum. Angular momentum makes it a lot more complicated to understand, but that's all there is. There's only that one extra parameter. The second thing is, we discussed this very special spherically symmetric case, and we found a singularity. Maybe that's an artifact of the symmetry of the situation. This was a real consideration when the black hole solutions were first discovered. Work of Hawking and Penrose shows that no, this is real. General relativity is a theory which, when you start with an initially smooth and reasonable non-singular space-time, you can prove that within a finite time in the future, or possibly in a finite time in the past, you had actual singularities. General relativity produces singularities starting from non-singular initial conditions, and then it doesn't know what to do, which means that general relativity as a theory is intrinsically incomplete. We know that we don't have the final word on gravity, and some of us are trying to do better, but at the moment, this is what we have. Do we need to care about what happens at the singularity? Well, again, we will never see anything that happens at the singularity at the center of a black hole because we don't see anything inside the horizon. There's this light-like surface surrounding it, and light cannot escape. So in some sense, maybe we don't care. There is a conjecture called the cosmic censorship conjecture, which is our model of Bayes, which says that all singularities are hidden inside horizons, which means things that are not described by the equations might be going on in your theory, but they're going on in places that have no causal effect on anything that's happening outside. We could go there and investigate them, though we'd never come back to tell, but they will never influence anything about us. The inside of a black hole has no impact on the exterior of a black hole. Nothing can escape, not even light. So this is the cosmic censorship hypothesis. There are indications that it may fail and that there may be such things violating it as singularities not hidden behind horizons. Those would be naked singularities. And there is recent evidence that such things are in fact possible in reasonable gravitational theories, but we of course have not observed any. In the realm of fantasy, let's look again at this image of the black hole that I showed you, where you remember that I described this as the outside of the black hole. This is the inside of the black hole. This was the singularity, and this was the horizon. This was the line R equals R Schwarzschild, which was light-like, in fact. And, this is the black hole. This is the outside. What is the rest of this? And this region, and I should note, this description is a description that is valid for a region just outside the horizon. That's why I was using it. but it's obtained by ignoring completely the fact that there's a star. You're basically using the solution to the part of Einstein's equations where you set the energy and momentum bit to zero, which is true everywhere outside the star. So those are the equations you solve to describe everything except where materials are. Most of space is free of matter and energy. It's mostly vacuum. And so we use those equations, and then you get that solution. You can extend that solution. So in real life, there would be a big fat star over here, and while you could hit the singularity, just like most of the matter in the star is, all of this stuff down here and to the left would be complete fantasy. But let's imagine we've drawn a valid solution to Einstein's equations anyway. We don't know how to create such a thing, but what does this look like? Well, so there's this region out here, which is the outside. There's this region out in here, which is the black hole. There's this region in here, which is interesting. Notice that you can't get into that region. No matter what you do, remember time moves this way, you would have to be moving faster than light to tip through this light cone. This is what's called a white hole. Everything can only come out of it. Nothing can ever fall into it. It's a time-reversed version of a black hole. And this region out here, it turns out, looks a lot like this region out here. So there is another asymptotic region, and away from the black hole it looks quite reasonable, like normal space-time. And so, remembering that time runs vertically, you now have this great description of two regions which the outsides that look like the outside of a black hole, which are disjoint, right? They don't touch each other, except at this one point they actually intersect, and this one point is just too short. The length of time that these two universes are connected, if you want, is just too short for a light beam to get from here to here. A light beam sort of can travel the boundary from one to the other. But this is the idea for what is called a wormhole. A small deformation of this leads to something called the Einstein-Rosen bridge, where there is a sort of finite time where the space-time on the right, space-time on the left are connected. That is the origin of the idea of wormholes. You can imagine that somewhere in our space-time is a horizon, and there is a sort of a length of time during which, by going through that region of strong curvature, you could come out into a completely different universe, or into a part of our own universe that is very far. You could imagine sort of our universe bending over in a wormhole cutting through or some such nonsense. And at the moment, we don't have any working solution, so the Einstein-Rosen bridge has been shown to be unstable. Any perturbation anywhere would collapse it down. People have been working on various ways to modify the solutions to get wormholes that are both stable and last long enough for at least a photon or a particle to get through, and maybe something macroscopic. That has not happened, but there is no theorem that I know of that precludes its existence, and so maybe there are solutions to the equations that generate wormholes, and maybe there actually are wormholes out there. I cannot exclude that. And then what's on the other side could be a different universe, could be a different part of our own universe. Going through a wormhole would be an exciting thing to think about. I didn't want to leave you without them. And then the last thing I wanted to discuss is quantum issues of black holes. And so it's a result, again due to Hawking, that quantum effects, the quantum fluctuations near a horizon, violate this idea that a black hole produces no energy. And in fact, a black hole does emit radiation. It's called Hawking radiation. It's not a property of general relativity, which is a classical theory. It's a property of the quantum fields, electromagnetic fields and electron fields and whatever other fields you have in your theory, fluctuating near, in the presence of the large curvatures at a black hole's horizon. And that means that a black hole radiates. And Hawking's calculation of the black hole radiation led him to later figure out that a black hole radiates black body radiation. A black hole has a temperature. The thermodynamics of black hole was later developed. It's quite a developed art, but it's a weird object. The temperature of a black body decreases with its of a black hole decreases with its mass. It's inversely proportional to its mass. Bigger black holes are cold. smaller black holes, less massive black holes, are hot. So smaller black holes, that means radiate more. This is very strange because when a black hole radiates, of course, the energy came from the black hole's mass, so the black hole loses mass, becomes a little bit smaller, and therefore a little bit hotter. A black hole is one of those weird objects with negative specific heat. As it loses heat, it heats up. Typically, objects lose energy and they cool. A black hole heats as it loses energy. So as it loses energy, it heats more, it radiates more. Remember T to the fourth. It heats more, it radiates more. So the end of a black hole's life would be a very dramatic explosion. In fact, the title of Hawking's paper was Cosmic Explosions, because he was thinking about maybe we should go look for these black holes that at the end of their life produce these very explosive, high temperature, large amounts of radiation. And black holes can completely disappear, evaporate. That's not a big worry, it turns out. The expected lifetime of a 5 solar mass black hole is on the order of 10 to the 62 years. Given a universe that is 10 to the 10 or so years old, that's not yet a major concern. But if there are tiny black holes around that therefore radiate more, we know about million solar mass black holes, those last even longer. We know about stellar mass black holes, those last too long. But if some mechanism produced 2 kilo black holes or proton mass black holes, those would evaporate much more rapidly, and the possibility of microscopic black holes and their evaporation is something that people are studying in various, both theoretical and at the LHC, even experimental level, to try to see if they can form a black hole and watch it evaporate, essentially, as part of their high-energy collisions. So this is the theory bit of the black hole discussion.